Imagine this. The James Webb Space Telescope pointed its mirrors toward the edges of the universe, and what it found sent shockwaves through science. Instead of a quiet, infant cosmos, it revealed galaxies far too big, far too bright, and black holes that shouldn't even exist. One of them, known as Li D568, is growing so fast it breaks the very laws of physics. It eats at a rate 40 times faster than the universe says is possible. And if that's true, then everything we thought we knew about black holes, the Big Bang, and even the origin of our universe might be wrong. Stick with this until the end, and don't forget to subscribe, like, share, and drop a comment, because this is the kind of mystery you'll want to talk about. Black holes were once thought of as science fiction, monsters lurking in equations, devouring everything in their path. But in reality, they're not just destroyers. They may be creators, architects of galaxies, keepers of cosmic order. Traditionally, astrophysicists believed black holes formed slowly. Stars lived, died, collapsed, and only after countless cycles of birth and death would galaxies and their central giants emerge. That was the accepted story, a neat one, but when James Webb's eye opened to the ancient universe, it uncovered something astonishing. Billions of light years away, meaning billions of years back in time, it spotted supermassive black holes already in place, already feeding, already shaping the cosmos. Mere hundreds of millions of years after the Big Bang. That's like finding skyscrapers in a village that hasn't even invented bricks. To make things worse, the luminosity, the blinding glow of these galaxies and their central engines didn't match the models. Galaxies should have been faint, scattered, fragile. Instead, they burned with the brilliance of mature universes. Scientists scrambled. Maybe it was a trick of the light. Maybe dust clouds fooled us. Maybe our equations were incomplete. And then came Lid 568, a black hole so voracious it breaks the Eddington limit, a cosmic speed limit for growth. If confirmed, it rewrites not just textbooks, but our fundamental understanding of reality itself. Because black holes aren't supposed to eat like this, yet here it is, feasting in defiance of physics. So the question isn't just how black holes grew so fast, but whether the laws we cling to are as solid as we believe. And if those laws bend, even slightly, what else might be possible? In the 1920s, a British astrophysicist named Sir Arthur Eddington laid down what became one of the most important boundaries in astrophysics. He showed that when matter falls into a star or a black hole, it doesn't just plunge inward. As it heats, it produces radiation, and that radiation pushes back. Imagine trying to pour water into a glass while someone blows through a straw at the same time. Eventually, the outward pressure matches the inward flow. Growth stops. This became the Eddington limit, a cosmic diet plan for stars and black holes. Too much food, too much mass, and the radiation literally pushes material away. It's why stars have upper limits on their brightness and why black holes shouldn't balloon instantly into giants. Astronomers used analogies like sails. A photon, the smallest particle of light, carries momentum. When it hits matter, it's like a breeze against fabric. Enough photons, and you've got pressure. That's the push that halts runaway growth. Wolf-Rayet stars, some of the most luminous in our galaxy, sit precariously close to this limit, shedding their outer layers like a candle melting too quickly. Now here's the issue. The black holes James Webb sees in the early universe don't seem to care about Eddington's law. They're not just glowing beyond what should be sustainable, they're growing beyond it, which leads to a paradox. If radiation pressure should halt their feast, how on Earth, or rather, how in the cosmos, did they become so massive so quickly? For LID 568, the numbers are absurd. It's feeding at up to 40 times the Eddington rate. Imagine someone eating 40 full-course meals in the time it should take to digest one. That's not overeating, that's metabolic insanity. Some scientists suggest short bursts. Maybe the black hole gulps food in furious episodes, then calms down, then gulps again. Others argue radiation escapes in focused jets, like a pressure valve releasing steam, so the black hole can keep eating. But whatever the mechanism, it's breaking a rule thought to be unbreakable. And when nature breaks its own rules, we should pay attention. Here's another puzzle. In the universe we see today, there are plenty of small black holes formed by collapsing stars, and plenty of enormous ones, millions or billions of solar masses anchoring galaxies. But there's something missing in between. The so-called intermediate mass black holes are astonishingly rare, like a ladder with missing rungs. If black holes were supposed to grow slowly, step by step, we should see these intermediates everywhere. Instead, it's as if nature skipped a grade, jumped straight from infants to giants. That gap itself is a clue. Some propose that in the dense soup of the early cosmos, massive clouds of hydrogen collapsed directly into black holes without ever forming stars. These direct collapse black holes could bypass the slow climb, shortcutting straight to the top. It's like going from a campfire spark to a skyscraper-sized inferno instantly. Elegant idea, but unproven. Others look at the role of dark matter. Maybe unseen halos of this mysterious stuff helped funnel gas into the hearts of young galaxies, supercharging their growth. But again, we lack direct evidence. This absence of intermediates haunts cosmologists. It's not just a statistical blip. It challenges the narrative of steady growth. And the existence of LID 568, already enormous, already shattering growth limits, suggests the shortcut wasn't just possible. It might have been the default. Picture this. In the early universe, conditions weren't like today. The cosmos was denser, richer in raw material, turbulent with collisions. If ever there were a time for black holes to cheat the rules, this was it. Perhaps we're not seeing a fluke, but the fingerprint of a very different physics at play in the beginning. And if that's true, then the missing intermediates aren't a gap. They're a message. A reminder that the path to understanding might not be a staircase, but a leap. Now let's focus on the star of this story, LID 568. Detected over 12 billion light-years away, it's not just distant in space, it's distant in time. We're seeing it as it was when the universe was less than 1 billion years old, and even then, it was already enormous. Astronomers measured its feeding rate and nearly dropped their jaws. The numbers screamed 40 times the Eddington limit. A black hole that shouldn't exist, existing. So how is it doing this? One theory is geometry. If the black hole's accretion disk, the swirling storm of matter spiraling inward, isn't symmetrical, then radiation can escape in narrow beams. Instead of pushing evenly against the infalling gas, it leaks out directionally, letting the feast continue, like steam escaping from a kettle through the spout while the water keeps boiling inside. Another idea, chaotic accretion. Instead of smooth, steady growth, LID 568 might binge in short, violent bursts. Imagine a compulsive eater sneaking meals in secret, overstuffing, then collapsing, then doing it again. Over cosmic timescales, that could add up quickly. And then there's the wild card. Maybe physics itself isn't what we think in these extreme regimes. If quantum effects or exotic matter alter the rules near the event horizon, then Eddington's law might not be universal. Maybe it's a guideline, not a law. The implications are staggering. If one black hole can break the rules, maybe others can too. Maybe the early universe wasn't an exception, it was the rule. And if that's the case, then the entire timeline of cosmic history shifts. Galaxies, structure, even the Big Bang narrative itself might need rewriting. LID 568 isn't just an object in the sky, it's a challenge, a cosmic dare. It's as if the universe is whispering, "You don't know me as well as you think." So what does all this mean? For one, it means cosmology. The science of the universe's origin is in flux. The neat story we told ourselves is cracking, and cracks in science are opportunities. Some researchers suggest energy we call dark energy, the mysterious driver of cosmic acceleration, could tie back to rotation or instabilities seeded by these early giants. Others wonder if black holes themselves generate space-time, making them not just residents of the universe, but builders of it. Critics, of course, remain skeptical. Extraordinary claims demand extraordinary evidence, but that evidence is growing. From gravitational wave detections to twisted light experiments in labs here on Earth, new tools are letting us probe questions once thought untouchable. Perhaps the most exciting part, these aren't just ivory tower mysteries. Students in small labs are already running tabletop experiments with lasers and photons that could shed light on the very birth of the cosmos. Imagine that, a beam of light in a classroom helping decide the fate of entire galaxies. We might not have final answers yet, but for the first time, we can see the path, and in 18 months, with new data incoming, we may know whether LID 568 is a lone rebel or the first glimpse of a new cosmic order. Here's where we're left. The universe is stranger, faster, hungrier than we dared imagine. Black holes, once thought to be the end of the road, might be the beginning. The Eddington limit, long treated as a cosmic wall, turns out to be more like a door. And beyond that door, who knows what rules apply? The story of LID 568 forces us to confront not just astrophysics, but philosophy. If black holes can defy the laws of growth, then what else might defy the laws we take for granted? Time, space, reality itself. One astronomer once put it this way: studying the universe is like listening to a conversation across a crowded room. Sometimes you mishear, sometimes you catch only fragments, but every now and then you hear something so strange. You know the conversation is deeper than you thought. LID 568 is that strange whisper. And maybe, just maybe, it's inviting us to listen closer. So here's the big question left hanging. If a black hole can break the rules of physics as we know them, what else out there is bending reality in ways we haven't even imagined? Right now, you've got a choice. You can click away. Forget LID 568 and go back to the ordinary. Or you can join a community that thrives on the extraordinary. Subscribe, hit like, share this with a friend who loves the impossible, and leave your thoughts below. Because the only way to uncover the universe's biggest secrets is to chase them together.